In this video, we're going to look at applying transformations to the graphs of trigonometric functions. First, let's remind ourselves about how transformations work in general. We start with a parent function like f of x is equal to the square root of x, and we can change the parameters of that function and come up with a transformed function like this one, g of x is equal to negative 3 square root of 2x minus 10 minus 1. To identify the transformations that have been applied to f of x to get g of x, we look at each of these in turn. And we need to remember, in particular, that we have to factor to make the immediate coefficient of the x positive 1 in order to identify all of the horizontal transformations. So before identifying any transformations, let's do that. We're going to factor that 2 out, which leaves us with x minus 5 inside the brackets and under the square root sign, and then we have minus 1 outside. Going from left to right, the transformations are this negative is a vertical reflection in the x-axis. The 3 is a vertical stretch factor 3. The 2 is a horizontal stretch factor 1/2, and we need to remember that in the horizontal dimension, things are counterintuitive or act opposite from how we might initially think. So this is not a horizontal stretch of factor 2, it's a horizontal stretch factor 1/2. And similarly, replacing x with x minus 5 gives us a horizontal translation of 5 units to the right, because it's negative 5. If it were x plus 5, it would be 5 units to the left. Again, counterintuitive. And then the negative 1 is a vertical translation, 1 unit down. So that's a quick review of transformations when multiple transformations are applied at once. If instead of starting with the square root function, we started with the trigonometric function f of x is equal to sine x, we could apply all those same transformations and come up with this transformed function. Notice that the parameters are the same, we've just changed the function that we're starting with, the parent function. Again, to identify all the transformations, we need to remember to factor that 2 out so that the immediate coefficient of x is positive 1. Then we would get something like this, which looks, again, very much like the transformed function g of x above. And in fact, of course, all the transformations to take f of x and get g of x in this case are the same as we got here. So we can see that we can apply transformations to trigonometric functions in much the same way as to all the other functions we've studied. We're going to find that when transforming trigonometric graphs, it's easiest to focus on what we'll call the 5 key points, the points that have x values of 0, 90, 180, 270, and 360 degrees on the original function, and take those through the transformations. It'll be helpful for providing us with a kind of anchor to look at how the function is going to look under the transformations. Let's look at some examples starting with vertical stretches. We're asked to sketch and state the amplitude of y is equal to 2 sine x. Let's start by scaling our x-axis by placing 360 over here. Half that will be 180. And then we can find where to put 90 and 270 degrees on our x-axis. We'll also put our y values of 1 and negative 1. And we can draw our original graph of y is equal to simply sine x with no transformations, our parent function. We know that the 5 key points are 0, 0, 90 degrees 1, 180 0, 270 negative 1, and 360 0. So we get a graph that looks roughly like this. Now, if we want to stretch all of the y values by a factor of 2, we're going to need to extend our y-axis labeling. 0, 0 is going to stay here. The point 91 will become the point 90, 2. 180, 0 will stay there because the y value of 0 when multiplied by 2 doesn't change. 270, negative 1 will become 270, negative 2. And 360, 0 is going to stay there. So we'll get this graph. So this is now the graph of y is equal to 2 sine x. The 2 in front acts as a vertical stretch, as we've seen with other functions, and the language that we'll use for trig functions is that affects the amplitude. Remember, the amplitude is the height of a crest or the depth of a trough. In general, then, given y is equal to a sine x or a cos x, the amplitude is going to be a. In the example that we saw here, a was equal to 2. So vertical stretches affect the amplitude. Now let's look at vertical translations, which are going to affect the axis. We're asked to sketch and state the equation of the axis of y is equal to sine x plus 1. If we draw the original function, y is equal to sine x, and it's good to get practice drawing these, we can put in our 5 key points, and then connecting them, we get a graph that looks something like that. Now, if we want to draw sine x plus 1, we're going to have to move all of these points up by 1. That's a vertical translation of 1. So again, we're going to need to extend our y-axis here in the positive direction. Note that we don't have to extend it in the negative direction, though, because these points are all going to be moving up. So the point 0, 0 is going to now become 0, 1. 91 will become 92. 180, 0 will become 181. 270, 0 will become, 270 negative 1 will become 270, 0. 360, 0 will become 361. So the function now is going to look like this. Notice that the axis of the function, the line around which the function oscillates, has moved up from y is equal to 0 to the line y is equal to 1. So vertical translations affect trigonometric functions in the same way they do other functions. If we look at it in general, applying a vertical translation of c is going to change the axis. So y is equal to sine x plus c, or cos x plus c, is going to have an axis with an equation of y is equal to c. Remember that because the axis is a line, it needs an equation, y is equal to c. Now let's look at horizontal stretches. We're asked to sketch and state the period of y is equal to cos 2x. Here we've changed to the cosine function to get a bit of practice with it as well. Again, let's draw the original function, the parent function, y is equal to cosine of x. We're going to label our axes, and remember that it goes 0, 1, 90, 0, 180, negative 1, 270, 0, and then 360 back up to 1. Looking something like that. Now, if we want to draw our y is equal to cos 2x function, we need to recognize that we've replaced x with 2x. This is a horizontal stretch factor of 1/2. Remember, because we're doing horizontal stretches, it's counterintuitive. It does the opposite of what we might initially think. It's not a horizontal stretch factor 2, it's a horizontal stretch factor 1/2. That means things are going to get squished in towards the y-axis. So going point by point, the point 0, 1 is already on the y-axis, so it's going to stay there. The point 90, 0 is going to move halfway in to 45 degrees 0. The point 180, negative 1 is going to move to 90, negative 1. The point 270 is going to move halfway in to 135, 0. And the point 361 is going to move to 181. So this is our new function, y is equal to cos 2x. So it's been squished in half that way. Now, keep in mind that this function is going to continue, so we could keep drawing the function and we could see that actually a second cycle would fit between 180 and 360. But here in the solid red line, we're just drawing one cycle of the function. Now, if we think about it, this 2 meant a horizontal stretch of factor 1/2, and we can ask, what's the new period? Well, remember, period means how far or how long does it take for the graph to repeat once, and we see that this is one cycle, then we start a second cycle. It takes 180 degrees to get through one complete cycle and start on the second. So we've gone from a period of 360 degrees in the original blue parent function to a period of 180 degrees in the transformed red function. In general, if we replace 2 with b, here b was equal to 2, and we think in the general case the graphs of y is equal to sine bx and y is equal to cos bx have been horizontally stretched by a factor, not 1 over 2 as in this specific case, but 1 over b. Here when b was 2, we were stretching by a factor of 1/2. If b was 3, we'd be stretching by a factor of 1/3. If b was 8, we'd be stretching by a factor of 1/8. Notice when we stretched in half, the period halved. It went from 360 to 180. So we multiplied 360 by our horizontal stretch factor. 360 times 1/2 was 180. And that gave us our new period. If we have a general horizontal stretch factor of 1 over b, that means our general period is going to be 360 divided by b. So we can work out period from the equation of the graph by looking at the b value and just dividing 360 degrees by that b value. As an example, let's say you were given the equation y is equal to sine 4x, and you wanted to know the period. The period is going to be equal to 360 divided by the b value, in this case 4. So we work out that the period is 360 divided by 4, or 90 degrees. And that makes sense if you think about it, because this 4 represents a horizontal stretch factor of 1/4. The graph has been horizontally stretched by a factor of 1/4, so it makes sense that its period is 1/4 of what it used to be. Here's another example, this one going in the opposite direction. We're asked to give a possible equation for a transformed sine graph that has a period of 120 degrees. This time we're given the period and we're asked to find the equation, which means we're going to need to know the b value. So we know that period is equal to 360 degrees divided by b, and rearranging this equation, we get that the b value is equal to 360 degrees over the period. We know that the period is 120 degrees, so b is simply 360 degrees over 120 degrees, or b is equal to 3. That means that one possible equation for this transformed sine graph would be y is equal to sine 3x. Again, this makes sense because if you think about it, this is a horizontal stretch factor of 1/3. The graph has been horizontally stretched by 1/3, so its period should be as well. Should go from 360 to 1/3 of 360, or 120. Let's look at horizontal translations, or phase shifts as they're called. And this is a term that you'll see sometimes more in physics. We're asked to sketch y is equal to cos of x minus 90 degrees. Again, let's draw the original untransformed cosine function. So we start from 0, 1. And we get a graph that looks a bit like that. Now, this is going to be a horizontal translation of 90 degrees to the right. Remember again, horizontal transformations are counterintuitive. Because this is minus 90, we're moving to the right. If it were plus 90, we'd be moving to the left. So each of these points is going to move 90 this way, or one major tick mark. So the first point ends up there. This point is going to end up here. 180 negative 1 is going to end up over at 270 negative 1. 270, 0 ends up at 360, 0. And this one is going to end up moving 90 degrees to the right, or at 450 degrees and 1. Now if we connect those, we get a graph that's the same shape as the original, but moved 90 degrees over to the right. And again, of course, this graph is going to continue going infinitely in both directions. So we could put that dotted line there and imagine that the graph keeps going like that. So that's a phase shift of 90 degrees to the right. Now, if you look at the red graph, you'll notice that by taking the cosine graph and shifting it 90 degrees to the right, we've got what looks like an untransformed sine function. So cos of x minus 90 degrees is the same as simply the sine of x function. And If we were to start from the red graph, the sine function, and shift it 90 degrees to the left, in other words, if we were to take the sine function and replace x with x plus 90, shifting it 90 degrees to the left, then we would get the cosine of x function. As you probably observed previously, the sine x and cos x functions are simply translations of each other. And otherwise, we see that horizontal translations of trig functions just obey the same rules as other functions do. Let's summarize by putting all of these different transformations together on one function. If we look at f of x is equal to 3 sine 2 bracket x minus 60 degrees plus 4, we can work from left to right. This 3 is a vertical stretch factor 3, and as we said previously, that's going to affect the amplitude. The amplitude of this transformed sine function is going to be up to 3 now from the 1 it started off at when it was not transformed at all. This 2 represents a horizontal stretch factor of a half, and we said that the period is going to be 360 degrees divided by 2, that b value, or 180 degrees. This graph, having been horizontally stretched in half, is going to complete a cycle in 180 degrees instead of the 360 that it started off with. Let's skip this for a moment, move to the 4. That represents a vertical translation of 4 units up, which means the axis, which used to be y is equal to 0, the x-axis has now moved up to y is equal to 4. And coming back now, we've replaced x with x minus 60 degrees. That means that we have a phase shift of 60 degrees to the right. So that's an introduction to transforming trig graphs. In the next video, we'll look at how to graph functions that have multiple transformations like this applied to them.